Alright, so let me start with the usual reminder to not use laptops and devices in class. Okay, so those of you who are still using it, please stop. So what we are going to do today is start with a very low level. Okay, what is going to happen when you boot your machine? How does the kernel start running? Okay, by and large, as far as the course is concerned, you are not going to modify much of what we talk about today, which are bootloaders and so on, but it's important to understand the process by which an OS boots up. Okay, and you will see that it's not very simple, somewhat boring and mundane, but it's something that you want to know as you get started, because eventually if you have to debug your kernel, you need to know how the boot process works and where your kernel failed to boot and things of that sort. Right. So basically what is being shown here is a 6-step process that your PC actually goes through in order to boot, from the time you power it on to the time your OS has actually booted up and shows you a login prompt. Okay. So we will go through each of those steps one at a time. Okay. So you will see that there are some steps that are really low level hardware steps, and then there are some that are really higher level software things. Okay, so let's start with the BIOS. BIOS, the acronym stands for Basic Input Output System. This is essentially the thing that turns on when you power on your PC. Okay. So it's essentially a piece of code that lives in firmware that starts running. It's going to do some basic checks, and then it's going to bootstrap the rest of the system. And what is shown there is essentially 4 of the steps that we will talk about. There are 2 more after that. So you will basically start with the BIOS. BIOS will then go to what is called the master boot record. You will boot something from there. It's going to go to an active partition. You will boot something else from there. Then you go to a bootloader, and the bootloader will finally boot the kernel. None of these steps actually have anything to do with the kernel. The kernel actually is the very last step in a boot process. Okay. So let's start with the BIOS screen. So if you have a PC that's still the old style PC, when you boot it up, you see a screen of that sort, where it actually prints some messages when you power it on. It will say it's doing some self test, and it will say how much RAM is there. It will start checking for peripherals. This is the BIOS trying to do some hardware checks before it actually does anything in terms of booting the machine. Okay. The modern incarnation of the BIOS is this. Okay, it does not show you anything. Okay, it just shows you an Apple's logo. Okay, but all of those things are still happening in the background, but most vendors do not want any users to know what is going on, so they just suppressed all that information. But the old style PCs would actually print all of that out. Okay, and some still do, but not all. Okay, but let's go through all of that, what is shown on that screen. Okay, so as I said, BIOS is the lowest level of software that is interacting with the hardware. Okay, it's, as the name suggests, it's called Basic Input Output System. It's also the layer that the OS is going to use to communicate with things like devices and peripherals and things of that sort. Okay. So it is not stored on your disk, it's stored in EEPROM, okay, read-only memory. Some of them are reprogrammable, but many of them are not. Okay, so it basically comes from the vendor. We don't actually change it, and it is designed for a particular motherboard and hardware and things of that sort. Okay. So, and it basically will use interrupts to write to disks and so on. So it's fairly low level. It's essentially firmware at some level. Okay. So when you power on your machine, it's going to do a power test. It's called post power on self test. It's going to initialize the memory. It's going to look for hardware. It's going to look for disks, things of that sort. And then once it's found the disk, it's essentially going to start the boot process from that disk. Okay. So this is step 1. Okay. Then step 2 in the boot process. Oh, that's interesting. Hold on. Something happened in the figure. All right. Okay. So that the first sector on every disk is called the master boot record. Okay. 512 bytes. Okay. Sector 0. Okay, that's always referred to as the MBR or the master boot record. The structure is actually shown in that figure at the bottom. Okay, and that's also described there in the slide. So it has some bootstrap code that is that's going to basically start off the boot process. Okay, the master boot record also stores the partition information. your disk may have multiple partitions. Okay, if you have a C drive and a D drive in Windows, those might be two partitions on the same disk. If you have boot camp on a Mac, you have two partitions, one stores OS X, one stores Windows. You can create up to 4 partitions. Okay, if you for that you have to repartition your disk. By default, most disks come with just one default partition that takes the entire disk space. Okay, but you can have more than one. And the master boot record essentially has this table, okay, which is these 4 blue boxes at the bottom, that shows you information about what the partitions are, what the partition sizes are, what the start address and the end address of the partition is, and so on and so forth. Okay. So, some bootstrap code and a partition table. Okay, if you actually go to Wikipedia, you will see lots of gory details of what is in that partition table, which is actually shown at the bottom here. Okay, you will see that it has the starting address, the ending address, cylinder and whatnot, which is all how you address the disk. Okay, each of these things is essentially a partition table, but the first 446 bytes is essentially a bootstrap code. So, fairly small amount of code that you can actually use to start your machine. Okay. So that's your bootstrap code. Okay, so the BIOS is going to essentially start reading from byte 0 of the master boot record, and then you will essentially start executing that code. Okay. And so there's not much in that code. It's just going to point you to what it essentially does is it's going to check the partition entry and say which is the active partition or the boot partition. Okay. Essentially, a disk needs a boot partition, which is the partition you are going to boot from. That's the partition that needs to hold your OS. Okay. Not every partition needs to have an OS, but there's at least one partition where the OS needs to reside. Okay. That's called your boot partition. Your partition table will actually tell you which one of it is the active partition. So, essentially that bootstrap code is simply going to look for scan the partition table, look for the default or active or the boot partition, and then essentially jump to that partition and start booting the next stage of the boot. Okay, so that's what is going to happen here. Okay. Now, so you have essentially now looked for a partition and then gone to that partition, and then this is what it looks like, which is, I guess the hex is not as important, but the first 512 bytes of that partition look somewhat like the master boot record itself. This is called the volume boot record, okay, also called the boot partition sector. Okay. So, the difference between the VBR and the MBR is that the master boot record is the first sector of a hard disk. The volume boot record is the first sector of a volume or a partition. Okay. But they essentially have similar structure. In a volume boot record, or also called the partition boot sector, you again have some bootstrap code, which you will see at the bottom here, but you also have information about the partition itself, saying how large is it, where does it start, and so on. So, essentially as far as our boot process is concerned, it is going to jump from the master boot record bootstrap code to the partition boot sector bootstrap code. Okay, and it will start loading those instructions. Needless to say, these are assembly instructions, okay, because you have only 400 bytes. You are not going to write some big C program and store it there. Okay, you have a question?
What's the need of multiple partitions?
Okay, what's the need for multiple partitions? It's just flexibility, because you might, as I said, want multiple volumes to keep different types of data. Okay. Typically, you might have an OS volume and a data volume. You might make your machine dual boot. You can have Linux and Windows, right? So, Windows will live on one partition, Linux will live on another partition. So, there are many reasons to have partitions.
Folders can also do many of those things, right? Different folders, you have different data.
Folders are inside that's a file system. Okay. This is actually at a disk level. So, you are essentially creating space to keep different things in there. Each partition can be a different file system, because Windows will use NTFS, Linux will use ext3, ext4. Okay, so, you may not be able to boot Windows from a Linux partition, for example, because partition file systems may not be supported across OSs. And so, there are many reasons. Okay. As I said, by default there is only one. Okay, that's the only machine, only OS that you have, and then you will have only one partition, but you can have more than one. Okay. Yes, question.
Does the GPT, does that work the same way as the MBR? Like, how does it work internally?
Right. So, I think there are many partition schemes. You are asking about a different way to partition. Okay, so that's another way just you are going to essentially have very similar information. You have a disk, it can have multiple partitions. You can then say where each partitions, the partition table is only going to say how many partitions are there, what the sizes are, what the start address is. Partitions are assumed to be contiguous on disk always. Okay. So there are many structures that have encoded partition table. GPT is one, MBR is a different one. MBR is old actually. This is how the Windows and DOS would boot, but it's still in use. If you have a USB key with the FAT file system, it's going to have this scheme. Okay, but there are other schemes as well. Okay, but the concepts are similar. The structure is different. How many bytes are for what field? That's what is different, but information is very similar. Okay. Any other questions? Okay, so you will see there's a second bootstrap code here. That's what you are going to essentially start booting. Okay, and that bootstrap code is essentially going to point you to, because that's an OS partition. So it's actually going to point you to where the kernel is stored. So you can actually start booting, not the kernel, but typically you'll have a bootloader that comes before the kernel, but you can point to either a bootloader or a kernel. Okay, so we started with the BIOS. From the BIOS, we went to the master boot record. You read that bootstrap code that pointed you to volume boot record. You read that code. That is now going to point you to a bootloader. Okay. So if you have used things like grub on Linux, that's a bootloader. Okay, I'm going to show you what that means. So essentially, this is called a second stage bootloader, because anything that you have on a MBR or a VBR, that's low level code, that's called first stage, but you might have two versions of the first stage. So technically this is third stage, but in literature it's called second stage. Okay. So what you are going to do now is essentially go read the bootloader, because that's what the volume boot record bootstrap code is going to point you to. So you will load that, you load some config files which tell you what the OS might be, and then you can boot. Okay. Of course, you don't need to have a bootloader. If the only thing you have is one OS, you can simply go and start loading the OS kernel and it will start booting. Okay. But typically you will have this bootloader stage as well, which allows you to boot multiple kernels and so on. So if you booted MINIX and it showed you should I use option 1 or option 2, all of those things are a bootloader giving you boot options. Okay. Then you use that to choose which kernel to boot. Is this clear? Okay. So your bootloader is actually, they're getting more sophisticated. Okay, you don't have to read all of that, but I'm going to go through 5 or 6 steps. It just tells you all the things that the bootloader has to do. Okay. First thing is the bootloader needs to understand the structure of the file system. Okay. Because if it doesn't know what file system it is on, it cannot actually read files, or neither the OS kernel nor the config files that are stored on that file system. So the bootloader by default needs to support the native file system that the OS uses. So if you have a multi-OS bootloader, it needs to understand NTFS, it needs to understand APFS, it needs to understand ext4 and things of that sort. So minimal drivers needed to understand the structure of the file system are essential. Okay, so the first thing it's going to do is essentially going to load basic file system drivers. That's step 1. Okay. Once you have that, then you can actually access the disk and understand files that are stored on that volume. Okay. Then you are going to go and load the config file for that bootloader. Okay. That config file is going to give you all kinds of options of what you need to boot and things of that sort. Okay. And then certain bootloaders might have extensible modules. That's something you can boot as well. And then once you start running, you display the menu saying what is it that the user wants to boot. And then once the user chooses an option, or if there's a default option, that is when you go start booting your OS kernel. Okay. So here's an example of a grub2 config file. You really don't need to understand much of this, but you will see that here is one of the entries. So that's an option that's going to pop up when you start booting the machine. You can have multiple entries. Each entry is one option that's going to be shown to you, and you can modify them if you want to add multiple options. Okay. If you make your machine multi-boot, you will have definitely a multiple option. But even on a single volume, you can offer a choice of kernels to boot from. Okay. This is the feature you will use as part of your kernel development, because you should always keep a stock kernel. You should not overwrite it with your kernel, because if your kernel is buggy and it crashes, then you can't boot anymore. Okay. So always when you are doing kernel development, keep a stock kernel. Then when you make your own, that is a second kernel, and then you just have two boot options, and if your kernel crashes you reboot, and then you pick the safe one and then you boot from there, and then you go fix whatever you need to fix. Is that clear? Okay, so that is grub, but you may think MINIX does not use grub, it has its own small bootloader, but the concept is similar. This is what is used in the Unix one. Okay, so this is the kind of screen you will see if you actually boot from grub. It will show you all these options saying should you want to boot here. This is just one OS, okay, all Ubuntu, but it is showing you different kernels to boot from, okay, as an example. Okay, so thus far you have gone through lots of steps, but we are still here. Okay, so in terms of OS hasn't even started booting. Okay, all of these steps actually happen before the kernel even gets loaded. Okay, but now that you picked what kernel you want to boot from, that is when you are actually going to start booting a kernel. Yes, question.
So you said that in grub the first stage was that we load the file system drivers. So are these implementations different from the implementation that you have in the kernel, or do the load, like are they able to access, or how is it implemented?
The file system drivers, how they are implemented. So the OS is going to have its own file system drivers. Grub may or may not use them. At a minimum it needs a very basic one, at least a read only one, because it does not need to write to the file system, it is just reading a config file. So you can make a smaller version if you want and make it available. Grub also has extensible modules, so you can actually add new modules and it will learn about new file systems and things of that sort.
Also, in BIOS we had the power on self-test stage. So is any of the information about which of these devices are connected or working, is it conveyed to any further layers, or it's just a test that's done it?
Okay. Question is when you did BIOS, you did a self-test, you discovered devices. So when the OS boots up, right, it is actually going to query what devices are present, and it might dynamically load drivers as well. Okay. First, something needs to know what is present on your machine. Do you have an external keyboard? Do you have a mice, or what graphics card? All of that is discovered by the BIOS, but the OS is going to query it, so it knows what hardware is present, load the drivers and so on. Okay. So that is how it is going to work. Any other questions here? Okay. So next step is essentially you select a kernel from the grub, and you start loading the kernel, and the kernel boot process is also somewhat interesting. So what it is going to do is when the kernel boots up, it does not necessarily have access to the entire disk and whatnot. Okay. So what it will do is it actually creates a dummy file system, okay, not a dummy, it's a RAM file system. It's a small file system separate from the real root file system. It's going to load that in memory, okay, and then it's essentially going to have some files that it needs to boot from there. So it's actually going to access those files, boot up, okay, and then it is going to actually use the root file system to do the rest of the boot process. Okay, so essentially, and I'm going to show you in just a second. So you're going to load an image that contains a small root file system, okay, and that is going to be loaded in memory. So it's not running off disk. You load the whole thing in memory. So that part of memory looks like a small piece of disk. It has actual files. You mount that file system. It has other modules you need to boot. So then you start booting from there. Okay, once you do that, then you actually go and load the real files. So it's a really bootstrap process. So you use a small file system, give the OS it the information it needs, and then you actually access the root file system. Okay. So you will essentially mount the image file system and then detect hardware, and then you mount the root file system. Okay. Once you do that, then you have access to all the files on your actual disk, okay, and then you will start the rest of the boot process. I'm going to just show you in just 1 second. Okay. So if you go to any Linux box, and I'm going to make this bigger, okay, and go to /boot, okay, so you will then see, okay, so you will see that there is this init RAM fs. Okay, so that's the file system. That's what is going to get loaded into memory. That image essentially is a tiny file system. Okay, it has some files. That is what the kernel is going to boot. Okay, and so that's your kernel. Okay, you see that this machine has several kernels. I'm not sure why. There are 5 or 6. So your grub is going to probably allow you to boot from any of them. Okay, and there's a root file system there. That's what is going to get loaded first, and then it's going to load your actual file system from disk. Okay, that's a RAMFS. I don't know if anybody knows what a RAMFS is. Has anybody heard what RAMFS is? No. Okay. So RAMFS is an in-memory file system. Okay, so it's not an on-disk file system. So most of these Unix operating system have this ability to take a piece of memory and construct a file system on it. Okay. Just looks like a regular file system, except that it's not stored on disk. It's stored in a piece of memory, but it looks exactly like an actual file system. Okay. Clearly, if you write to it and then you don't save it later, it's all going to go away because it's volatile. Okay. So you can essentially take a piece of memory and say this is a file system. Maybe you basically have slash and some files in there. Okay, and then you can just access that file system as if you're accessing an on-disk file system. Yes, question.
Does the INIT RAMFS itself have like an X file system in it, or is it some kind of like other archive format that just has files?
Right. The question is, does it have actual file system in it?
Like, does it have? Is it like an image of an X file system, or is it like its own?
No, it is. You will see that it's an image. So it actually is a small ext file system. Right. So you just boot it up. It just looks like a normal file system. It just doesn't live on disk because the whole thing is actually stored in memory. So you just read and write to files in RAM. Okay. RAMFS is an abstraction that's used for many other things. It's used in the boot process, but if you want to have really fast I/O, you can keep your entire file system in memory, and then you have very fast I/O. So there are some databases that are in-memory databases that will use these kinds of concepts. But by and large, you don't actually store files in memory because memory is not persistent. You store them on disk. Yeah, but all Unix operating systems, and so does Windows, they support this notion of RAMFS, and this is actually where it gets used when you boot your machine. Okay. Any questions here? Okay. So okay. So once you have booted your kernel, then you start loading all the services that you want to start with the machine. Okay. And that is done through a process called INIT. Okay. There is a script. So you are essentially going to call an INIT script. Okay. That's the last second to last stage of the boot process. Okay. So you are going to essentially call this file INIT. Okay. It's and on some machines it's now called systemd. Okay. This is the file that has scripts that start all kinds of services. Okay. So you will start DHCP service, then it's going to go ask for an IP address, you will start SSHD, whatever services you need to start are essentially started by INIT. Okay. And the way INIT works is INIT just stands for initialize. Okay. So there is a file called init tab. Okay. That's basically going to have some information that INIT is going to use to decide what services to start. Okay. And you can call INIT with one of 6 different options, which are called run levels. Okay. They are just numbers. Okay. Run level says what is it that the user wishes to start. Okay. Sometimes you will see it's also stop. So run level 0 just says halt. Okay. Halt, that's to shut the machine down, not to start. But essentially, when you're starting up, there are 3 run levels that are important. Okay. Run level 1 is single user mode. That means that you'll just boot a minimal OS that just allows the root user to access the machine. You can, or no other user can access the machine. That's only used for system maintenance, debugging, and so on. Okay. The default run level is run level 3. Okay. That's your standard multi-user mode. Okay. So when you boot up, it will start SSH. Other users can log in and so on. Okay. There's also init level 5. Init level 5 says start in multi-user mode and start X Windows environment. So there's a graphical user interface login to your machine. Okay. And then run level 6 is again shut down. Okay. So when you start your init or when the kernel starts init, it needs to know what run level you are starting on. That's stored in init tab, and based on that number, it's going to decide what scripts to run. Okay. And corresponding to each run level is a directory on your machine. Okay. That's a directory in something called /etcrc.d. Okay. You will see there's a rc0.d and 1.d and 2.d. Each of those directories store startup scripts. Okay. In some cases, they are shutdown scripts, but these are startup scripts, and so depending on the run level, you go to that corresponding directory and you just run all the scripts in that directory. Okay. So run level 3 will have something like start the networking services. So it will start DHCP, try to get IP addresses, you might say start SSH. So, any service that you want to start at boot time needs a corresponding script in your RC directory at the right run level. Okay. So, again we can take a look in this machine here. So, you will see that there are all these directories. So, if you want to go into rc3.d, so you will see that these are the services it is going to run. Okay. So, it is going to run the networking service, and then it is going to run SSH service, and there are a bunch of other services. Okay. So, if you want to start a new service, that is where you need to add a startup script, and then when your machine starts up, it will automatically execute that script and start something up. You have a question?
These are just regular programs, though, right? Or is there something special about these?
These are all system services which run as user level processes, right. So, they are not part of the kernel. Kernel is booted up, it started init, init is starting all other services. Okay. So, needless to say, init is the first user level program that starts up. So, if you look at the process tree hierarchy on your machine, okay, you will see that init will typically have the smallest process ID. Okay. So, if you go into a Linux machine and type ps tree, okay, that shows you the process tree on that machine. Okay. So, here init is called systemd, okay, but that is essentially the root, not the root, but it is at the top of the process hierarchy. You will see that everything else has been started from root, okay, or systemd, okay, including the shell that you are on and so on. So, this is going to just show you the structure of everything that is running there. Okay. So, you will see that there are all kinds of things running. You do not really need to worry what they are, but you will see the parent child relationship between all the processes that are running, and at the very top is your init. Okay, I am going to show you the same thing on MINIX in just a moment. Okay. The other minor detail which you really do not need to know is the file names, okay, have a naming convention in rc.d directory. Okay. If you start something with an S, that is a startup script. If you start something with a K, that is a kill script, that is for shutting something down, and there is a number after an S or a K. Okay. So, if you say S12, that is assumed to be the 12th script that starts up. So, essentially you start them in order. So, if you want to order saying you better get an IP address before you start SSHD, because if there is no networking service, you cannot start a SSH server. So, you always want to number them in a particular order to capture any dependencies. Okay. So, that is and then essentially you are going to start them in increasing order. They do not have to be consecutive numbers, because these are just file names. You are just going to sort them in order and then just execute one script at a time. Okay. All right. So, now you have run level services. So, now you are done. Okay. Your machine has actually booted up. So, we went through all of these processes, as you can see. So, it is a 6-step process. Okay. The OS actually starts at step number 4. Okay. And that is the only step you really have to worry about. All the rest you do not really care as far as this course is concerned, but you need to know it was all happening in the background. Right. Okay. So, this has been either somewhat generic explanation or Linux specific, okay, but this you are not going to start with Linux, you are starting with MINIX. So, I am going to translate how these concepts are going to apply to MINIX. Okay. Next. So, let us start with MINIX. Okay. So, that is essentially this table which is taken from the book essentially shows you what is in the boot image that you have when you compile a kernel and what is stored on the file system. Okay. So, the boot image or the kernel essentially has the microkernel itself, but some of your servers are essentially part of the boot image. Okay. So, when you boot, they are all part of that image. So, you can just start those programs right away. Okay. And then you will see some other things are part of RC scripts. They started once the machine starts up, or a kernel starts up, you have an init process that is going to start them up. Okay. Now, what goes in the boot image, what stays outside, that is a design decision. Only thing you really need in the boot image is the kernel. Everything else could have been outside. Okay. But the way MINIX is structured, they put some things directly on the boot image. So, when you start or you load the image, all the programs are in there already. Okay. So, that is first thing you want to keep in mind. Okay. Now, the process of starting MINIX very similar to what I just said. Okay. So, you will see that sector 0 essentially is your master boot record. It is going to point to a boot program, that is essentially a bootloader. Okay. And then you will see now that if you have multiple partitions, exactly what I showed you, but now laid out on a disk. Okay. So, what I showed you in the table, it is the same thing. You will see here that there are two partitions, this partition 1 and partition 2. Each partition essentially has a boot loader and a boot program. Okay. If you just had one, then it would look like this. Okay. If you have multiple, then you have to have a partition table and you need to have a bootloader for each partition that loads whatever is on that partition. Okay. So, here are some boot options. So, as you will see, when you boot your MINIX kernel, you have something equivalent to grub. You can essentially say boot this kernel. Here are the parameters, because the kernel can take command line parameters that you can see what to use. By default, just go with what is in there, unless you need to change something. Okay. So, there is a very similar process in MINIX, and I am going to boot up a MINIX VM and show you. Okay, there is essentially a RAM disk. Okay, it is essentially stored in that directory. You do not really need to worry about it. When you compile it, it all gets compiled. Okay. Unlike Linux, we do not have separate RC directories, because MINIX is very small. Everything is just stored in one script, okay, which is essentially in /etc/rc, and you just boot whatever is in there. So, you do not have concept of many users and all that. It just by default just starts at that level. Okay. It is much smaller OS, so simplifies a bunch of things that you actually would see in a more general purpose OS. So, I am going to show you a few things here. Okay, so let us start this thing. Okay, so this is your bootloader. Okay, so it is going to boot something. Hopefully, it will start. Okay. So, it is essentially starting some script, just checking, and now it is booted up. Okay, so all of these things are essentially part of your RC script. So, you can check the integrity of your file system, you can start networking services, all of that happens here. Okay. So, now I just want to first show you all the processes that are running. Okay. So, if you see this, that is the process list, okay, and I believe it is sorted in order. So, you will see essentially there is a kernel. Okay, there is part of the kernel that shows up as some separate task, but then you will see the process manager, the file server, the reincarnation server, memory manager, all of those started as processes. The kernel essentially seems to have a negative process ID. I do not know why they gave a negative one, which could have started at 0, but it has a -1 PID. Okay, and then some of these other tasks, which is the system task and the clock task. Remember, I said they were all part of the kernel last time. They also have a separate process ID. They are like threads within the kernel. Okay, so, they basically show up as tasks or processes, okay, not real processes, because they have negative process IDs, but they look like processes. Okay. So, you will see essentially here is the init process. Okay. That is process 1. Okay, that is essentially started everything. Okay. So, it has the same process structure as everything else that you see on Linux. Okay. That is one thing you want to keep in mind, and then you should go, just so that you understand how all of this works, go and look at the /etc directory, which has a bunch of files. Okay. So, you will see that this RC okay. So, that is the file that starts everything up, and it has a bunch of, it does not do much, it just goes and starts another script. Okay, and some of these are stored in eventually where you end up is there is a system.conf.d. No, not this one. It's another one here. Okay, defaults. Okay, so you end up with okay, so these are all the this is your RC script. Okay, that's essentially going to start up all kinds of services. You don't really need to change this. I think you will make one change though, which is in the first lab you are going to start your own process, which will become a system process. So you actually have to add it to some of the script to start it up, to give it the right privileges and so on. So you need to know how to start up a system service and how to give it the right privileges. So you are going to make some changes to this file, maybe add an entry to start your own process. Okay. The other thing you should know is this other. So this file /etc/system.conf is an important file to keep in mind, because that is where for every system process you tell the system what is allowed and what is not allowed. Okay. So you will see here that it will say for the reincarnation server all IPC messages are allowed, all kernel calls are allowed, etc., etc. Okay. And you can then even say there will be some others where you are more limited access. Okay, so here you will say only system IPCs are allowed, but not all IPCs and so on. Okay, by default, when your process will start up, it will have no writes. If you try to do a kernel call, it will fail because it hasn't been given any rights to make kernel call. Unless you go into this file and say that my process actually has some rights, your OS is not going to, its security model will disallow, because it will look like a normal user process. It's not allowed to make any kernel calls directly. Okay. So you got to actually understand the structure of these files and try to see what rights you need to give to your process so that it can do whatever we have asked you to do, okay, which is make a kernel call and then do something with it. Okay. So you need to understand some of these. None of this actually has a lot of documentation, unfortunately, but it's also not hard to understand once you know that this is what you actually need to do. Okay. So I just wanted you to know this, because you will have to go and start modifying things and whatnot. Okay. Any questions on this? Okay, I left a lot of time for discussion, but there's no questions at all. All right. So let me say, so you can go read this and so on. You will see that there are all kinds of interesting things you can do. There's some man pages for it as well. Okay. I do want to show a couple more slides, and then we can have discussion of the lab and whatnot. Okay, so once you booted up your machine, it's going to look like that. Okay, that's the RAM layout. That's you basically started loading all kinds of things. So you have essentially kernel loaded there. You will have the disk task, the clock task, the memory task. So all of these are loaded in memory. Okay, and then that figure continues on the next slide, and then you essentially at the top part of RAM is where you are going to load your user processes. The bottom half is the kernel plus all OS processes. Okay, they are loaded in order, and then you essentially start loading your user processes. Okay, so that is what is going to be in RAM once you have gone through the entire boot process. Okay, you essentially bootstrapped and then brought everything to RAM, and you can start executing things. Okay, so let me take a little bit of time to talk about the lab. Okay, so the lab is essentially going to have, but let me first pause and see if there are any questions about anything I said. Okay, so we just covered the boot process. Okay, somewhat mechanical and mundane, but you need to know all of this. Otherwise, if your machine doesn't boot up, you won't know what to do or what to look for. Yes, question.
So let's say the master boot record gets corrupted, like how do we generally fix it, because it's outside the kernel and
Okay, so if the master boot record gets corrupted, how to figure? I mean, you can of course recreate the master boot record, but you need to know what is the bootstrap code is the easy part. If you have partitions, multiple partitions, the size of those partitions will be lost. You will not be able to recreate that. If there's only one partition, you can just rewrite to the master boot record and just set the partition size to be whatever 1 through the end of disk and things of that sort. But that's a very key sector. If you corrupt it, most of the time your machine will not boot anymore.
so generally we flash it with like a correct one and
When you format your file system, I'll show you some things as well. When you format your file system, the master boot record actually gets created. Okay. So, if you have a Mac and if you have a Linux, I will send you on piazza equivalent command, but if you have a Mac, you have a GUI, you can just start disk utility, because you just right. So, here what you have to do is you basically go and say create, I do not have a, I wanted to bring a USB disk and show you, but I forgot it in my office. So, what you can do is you essentially reformat it, and then when you reformat it, it asks you what scheme you want. You can choose master boot record or GPT and lot there are other options. So, that is when your master boot record gets created. Okay. And typically, unless you are repartitioning your disk, which some utilities allow you to do, but by and large most utilities do not. There are advanced ones that do, you do not change it. Okay. So, it is created and it just stays there as is. So, it is something you do not want to touch typically. Okay. Any other question? Yes.
Just a question, like if the first, like the MBR sector is like physically damaged,
Yes.
does that mean the whole disk will be unusable? Or is there
Yeah. Question is, if the master boot record is physically damaged, is the disk. So, if the master boot record is damaged, you will not be able to boot from that disk. Does not mean the disk is dead, right. So, disk is still alive. So, you could certainly boot through some other means. You can use a USB key to boot, you can have a live image, boot, and then all the data on your disk is still available, you can copy it out. But yeah, you will not be able to boot unless you have a repair utility that fixes it for you.
the partition information is not there?
Yes, the partition information not there. If there is one partition, you can still do something. If you had 4 partitions, that information is lost. So, you cannot actually go figure out what is going on. I mean, there may be utilities that just go scan everything, because the start of every partition has a certain information in it. You may be able to recreate that through a disk repair tool, but that is not a guarantee that it will always work, right. So, here is the, so you will see that there is a there are some byte values that tell you that here is a new volume record and things of that sort. So, you can go and figure out does this look like a legit volume record, then you can say maybe here's a new volume, but you will have to scan the entire disk looking for this and try to reconstruct. It is not an easy process, it may not always work. Okay. Anything else? Okay. So, as far as the first lab is concerned, okay, so that lab 1 is going to be given out on Thursday. So, I am going to spend part of the class on Thursday to cover concepts that you need to know to actually do the lab. But what I am going to do now is just tell you what the lab is about. Okay. At this point, you do not know enough to do the lab that I am going to start talking about on Thursday. Okay. So, first thing is labs you can have either a group of 2 or individual assignments, because you can do whatever you want. If you feel like you want to do it yourself, fine. If you want to team up with somebody, that is fine as well. Okay. Maximum group size is 2, not 3. Okay. So, keep that in mind. Okay. So, the lab starts with system calls, and it requires you to add kernel calls, and it asks you to actually implement a system process. But let me explain what each of these things mean. Okay. So, as far as if you remember the picture I had put up last time, okay, maybe 2 classes ago. So, the structure of MINIX is you have your microkernel, okay, and then you have user level processes. This could be a driver, okay. This could be your file server process, this is the process manager and things of this sort. Okay. So, these are system processes, and then you have user processes. So, okay. So, you can run whatever programs you want in user space here. Okay. Unlike a normal operating system, where the system call interface is the interface exposed by the kernel, okay, in MINIX the system call interface is not implemented by the kernel, it is implemented by the system processes, okay, and exported to user processes. Okay. So, this interface is the syscall interface. Okay. So, essentially a user process, when it makes a syscall, it comes to one of these processes, it does not go to the kernel. Okay. So, keep that difference in mind. In Linux, if you actually make a system call interface, okay, the picture is going to look like this. You have Linux and you have user processes. This interface here is the syscall interface. You are directly invoking the OS. Here you are invoking a system process, not the OS. Yes, question.
In Linux, the system call is software interrupt, and then the kernel will be the interrupt handler. But you say the kernel want to handle system call anymore, so
So here we haven't, the kernel is not involved in system calls. System calls are handled by system processes. Like if you want to create a new process, you call fork. Fork is implemented in the process manager. We'll get to that next time. Okay.
so that process become the interrupt handler.
Okay. So how the system? Yes. So you are asking how a system call is triggered. Typically in Linux, when you make a system call, it creates an trap. Okay. Interrupts are hardware interrupt. Trap is a software interrupt. Same concept. It is going to make a trap. The trap will actually cause the kernel to run, which will handle the system call. Here, lots of things are done using messages. Okay. We will see how all of that works. In fact, you might actually just send a message rather than causing a trap. Similar concept, but you don't. At this point, let's not worry about that. Okay. We'll get to all of how this works next time. I'm just describing what the lab assignment is, not how to do it. Okay. That we'll get to next time. Okay. So that's your system call interface. Okay. So all of these system calls have to be collectively implemented by the system processes. Okay. Now there is also a kernel call interface, which is the actual interface that is now exposed by our microkernel here. Okay. So that's your kernel call interface. Okay. In the MINIX world, okay, user processes make system call, system processes make kernel calls. Okay. User processes don't directly invoke kernels. Okay. And the reason you can do that is that sys.conf file, the system.conf file I showed you, actually denies the ability to make kernel calls to user processes. So by default, if you try to make that call, you will be denied. Okay. You will not be allowed because you don't have rights to do it. Okay. So this is the way things are structured in MINIX. Your goal on the assignment is first to implement a new system call. Okay. And if you actually Google for MINIX system call, you will see that there are all kinds of tutorials that tell you in excruciating detail how to do it. So go to this file, add a new entry, go do this, and so we will give you the same kind of help. So it should be fairly straightforward. You just follow the recipe, but try to understand what's going on. Just don't blindly execute the steps and you have no idea what you just did. That's not the goal. The goal is to actually get you started a bit more gently and then get you into the more in-depth part of the lab. Okay. So we'll first implement some system call. I don't remember what it is, but you will do one of those system calls. Okay. Then the second thing you will do is implement a new kernel call. Okay. This actually requires that you go and add something to the kernel. System call did not require you to do a whole lot to the kernel. You could add a new system call, for example, to a process manager. Okay. It doesn't need you to do anything to the kernel really. A kernel call does actually require you to do something to the kernel. So the kernel call is equivalent to a Linux system call, which requires you to change the kernel. Okay. So you'll implement a kernel call. Okay. That's the second part of the lab. And the third part is now you want to implement a new OS component. So you're going to write your own server. Okay. And I'm assuming that what the server will do is actually invoke that kernel call, maybe get some information to the kernel, and then you can essentially use a user process to talk to it, probably through that system call you just built. Okay. What the calls are is not as important, but what is important is two or three things. First, you now added an extension to the kernel by adding a kernel call. The second is for you to understand how to add a new component to the OS. You just write a new user program. It's literally just write a standalone C program. You compile it. Okay. You give it some privileges, and it becomes a system process. So writing OS components is as simple as writing user level programs. So that's a very nice thing because you can now extend OS functionality without necessarily touching the OS itself, unless you need new kernel calls. That's the only time you actually have to touch it. Otherwise, you can do whatever you want with the current interface. Okay. So you will write this new component, then you will have a user program talk to it. It will make some either that kernel call or some other kernel call, get some information, and you built a new system service. Okay. So that's what the lab is about. Okay. So you will touch part of the kernel, but the rest of it actually is just touching user level processes. Any questions on this? Yes. When is it due? We don't know yet. I'm thinking 2 weeks. I'm trying to get somebody to actually do the work, see how much work it is, and then decide. Because the first time we are handing this lab out, so I don't know the level of difficulty. I'm assuming 2 weeks, but we'll tell you on Thursday. Okay? But it shouldn't really take 2 weeks, but we'll give you 2 weeks. Any other questions? Okay. So that's the lab. So what we will do Thursday is actually go through the process of how system calls work, how kernel calls work, go back and look at few of these user level servers, understand them a little more. Okay, then you will have enough information to do the lab. Okay. In subsequent labs, we'll go and add new functionality to. You're not going to keep writing new system services. The goal is to understand the ones that are already there. So you'll go and start modifying existing ones and maybe extend the process manager or the file server and things of that sort. Okay, those are subsequent labs. Okay, we'll start with system and kernel calls as lab 1. Okay, so if you haven't finished lab 0, please do. Okay, because the real lab is going to be out in 2 days. Okay, so I'm here for more questions. Otherwise, we can end it early. I'm happy to stick around, answer any questions you have. So, okay.